In part 2 of the series, we're going to finish up where we left off in the MapReduce code walkthrough. So in the first part, we have looked at the Hadoop jar job submittal command, and we took a line-by-line walkthrough of the driver code. In this lesson, we're going to look at the map code, again line by line. We'll look at the reduce code line by line, and then we'll actually run a job submittal to see a job actually functioning and running through the Hadoop system. So on the required and suggested, actually we only have one requirement. Pretty much everything else that you've done to this point should be enough to prepare you for this video. And let's go ahead and look at the source code. Again, you will need your Cloudera Manager 4-node cluster or your Quick Start VM up, and hopefully you just left off where we left off in the last exercise, which was right here. We had looked at the wordcount.java driver code. So let's go ahead and close this. And now let's look at the word count mapper code. And again, I'm just going to use Emacs. You're welcome to use any text editor you like. You can push Control X1 to get a single windowed view. And again, this is our entire driver code in this one single window here. So again, at the top of our code, we have our Java imports. You can see that we're using just standard Java IO exception because the map method of our mapper class can throw an IO exception or an interrupted exception. We're going to use our string tokenizer. This is what's going to allow us to parse out the individual words in each line of our value that's coming in. We're specifying all of the Hadoop IO classes. Again, these are Hadoop specific classes, the last two imports. And then we specify our mapper. We're going to need that because we're going to extend the base mapper into our individual word count mapper class that we use here. And you can see that this mapper accepts 4 Java generics. This is a pretty common pattern in Hadoop that we specify the input, key, and value pairs, and then the output, key, and value pairs. In this case, we're specifying the data types for each. So if you remember, the file input format that we used in our driver code passes for its key the byte offset into the file or into the data set of the individual line, and then for the value, it passes each individual line, new line, delimited line, into the mapper. So this is going to be the key and value pairs that we consume. In this case, for our file input format, we do something that's pretty common with Hadoop. We just throw that key away. So the byte offset into the file is actually used because most often it is a throwaway. We don't worry about doing anything with it. And then we need to specify the output, key, and value pairs that we write out of the mapper. The type is going to be text, and the value is going to be int writable. The text actually is a writable type, and this specifies the serialization format that we use to write the data back out for writing to disk as well as transferring over the network, and it's actually a writable itself. So if you remember, our mapper is consuming, again, the key is the byte offset into the file. The value is each line of text, new line, separated line of text. And then our output key and value pair are different. We're outputting the actual word that we found. For each line, we're going to output one or more words. And then we're going to output a 1 each time that we run across a single word. So you can see here our key and value pairs do not completely match. Our input key is different than our output key, and our input value is different than our output value. Here at the very top, we're specifying some basic variables that we're going to use. We set up this 1 as just a new int writable. This is setting it up only once for this class. We don't need to create a new variable each time that we run across our map function. And then our text object, we're going to create a new text for every run of this entire function rather than every call of the actual method inside. So here you see that we override. This is the whole purpose of extending our mapper class, is to override the map method. And you'll see the same pattern in the reducer, that we extend the base Hadoop MapReduce reducer class, and we override the reduce method. And this is a very common pattern as well. Our inputs to this map method are going to need to match the input key and value types of the generics for our class. So again, you see that our long writable, our byte offset into the file, matches the input generic that we have, and our input value matches the input generic as well. Every time Hadoop calls this map method on our behalf, it's going to pass this context object. And this context object is what we use to write our data back out. Again, this is in CDH4 or Hadoop 2.4. You can see that we again throw possible exceptions. We possibly throw an IO exception or an interrupted exception in this map method. We take our input value and we first make sure it's a string and we put that into a line parameter, and then we run our string tokenizer over this line to pull out all of our individual tokens separated with white space inside of there. So once we have a tokenizer object, we can simply call has more tokens on it, and then we can set the word to the next token in this token list. So this basically takes every single word in this line and sets it to this word parameter that we had set up before for our text object. And then we output a single text type. So again, this needs to match the type of this variable, which is word, which is text, needs to match the output key that we specified as our generic. And we see that that does. And then our output value needs to match our output value generic, which is an int writable, which again, it does right here at this one parameter that we set up. So again, this is probably a pretty common error that you're going to run across as a beginning Hadoop developer, is just simply making sure that all of these parameters match. And if you remember in our driver code, we needed to specify the types for these as well, at least for our output key and value pairs. So for our mapper, it doesn't matter so much because it's not our final job output. In this case, our reducer is our final job output. We see that all of our types for this matchup, and again, our whole goal here was every time we run across a word, we simply output 1. So our mapper is just simply outputting 1 every time it encounters a word. And then our reducer is what's going to aggregate all that together. Let's go ahead and close this window and actually take a look at our word count reducer code. And let's open that up. Again, I'm using Emacs. You can use whatever text editor you like. Expand this window out a bit so we can see everything, and push Control X1 to get a single window. And again, you see all of the code that we need. So again, our code for a MapReduce job is typically not a complicated thing. We see a couple of Java imports at the top, our IO exception, again, which is what's thrown by our reduce method, as we saw with the map method in our mapper code. An iterator object, this is something new that we're going to need. Basically, if you remember, the reducer is receiving a text object as the key, so it's going to get a single word, and then it's going to get an iterable as its values. It gets a list of values that it's going to then parse over. So this iterator that we're applying here is this value that we're getting back in, and we're parsing over that. We also include our basic IO classes that we're going to use, and then we use a reducer import so that we can extend the base reducer and override this reduce method, as we extended the base mapper and overrode our mapper method. So again, you guys probably already know what this is. Our text is our input key. Our int writable is our input value or list of values. And then our output key and value is a text for the key and an int writable for the value. In this case, our input key and our output key are the same, and our input value and our output value are the same. But it doesn't have to be, even for the reducer. Again, our whole purpose of creating or extending this base reducer is so that we can override this reduce method. And that's what we're doing right here. Our key value pairs for our input need to match. So in this case, our key is a text type. We're calling that key. And then our value is a iterable of int writables. So this needs to match that. And again, it is an iterable for the reducer, because it's going to take all of the values across all the mappers and combine them into an iterable list. We see a pass of this context object, Hadoop. When it's calling the reduce method, will pass this context object for us. And we know from the mapper method that it is the same thing it's used to write our key value pairs back out. And again, it can possibly throw a couple exceptions. Because we're going to create a new sum of word counts for each word that we encounter, every time this reduce method is called, again, it's going to get a single word and a list of all the number of times that that word appeared. For example, in our hello Bob, it's Bob again, we would see hello and then a list which contains a single value, which is just 1. If hello was found across more documents, it would contain many instances of that 1 over and over and over again. We're initializing our sum or our final output to 0, and then for our iterable list of values, we're parsing over each one, and then we're simply taking the value, the actual number of the list, which in our case is going to be 1 every time, and we're adding it to the existing sum. So we start at 0, and then we simply keep adding the value over and over again as we encounter new values in our list. And then finally, at the very end, we output our key, which is just a straight pass-through. It's the word that we encountered. And in this case, we're going to create a new serializable type, a new int writable, and we're going to use some integer that we calculated before. Hadoop requires that each key is a writable comparable type, and that each value is at least a writable type, which is serializable. The keys also need to be compared because Hadoop, if you remember in the reduce phase as well as the mapper phase, it does a sort based on key. So we can see that our key is actually a text type, which is an int writable comparable, and our output value is an actual int writable. In this case, it's a sum. We've looked at our map code, our reduce code, and in the previous exercise, we looked at our driver code. So let's go ahead and compile some code here. So the next thing we have to do is go ahead and create our .class files. We do that with a javac command. We're going to specify the class path that we need. We need to specify all of the Hadoop classes. So we're going to, again, in backticks, put Hadoop class path, and we're going to compile up all of our .java files and let it spin for a couple minutes there. And if you see what it created, it now created these .class files for each. So we're halfway to having a jar file. The next thing we have to do is create a jar file. We're going to do that with a jar command, and we're going to specify cvf to put it in a single jar file. And in this case, we're going to specify we're going to create a word count.jar file out of all of our .class files. And again, this should happen pretty quick. Simply just took these files and combined them into a single jar file. So again, if we look at what we have here with an ls command, we see now that we've created a word count jar file. We can go ahead and submit this into our cluster, and let's do that now. We specify that with a Hadoop jar command. The next thing that we pass in here is the name of the jar file itself, so word count.jar with the .jar at the end. The next thing that we pass in is the name of the class that contains our main method. And if you remember our driver code, our word count.java actually had a word count class inside of it. So we just specify word count. We don't need to specify a .class after it. We next specify the input path. So in this case, we're going to specify input data/Shakespeare, which we should have gotten in there from the previous HDFS exercise where we put data in. And then for an output path, let's go ahead and specify output word count. And if we go ahead and push enter, we're going to kick off our job. So now Hadoop is going ahead and submitting this job into our job tracker, in this case into our local machine. We see that we have 4 input paths that we're going to process. And now our code is simply chugging through and running the map function. And you'll see the percentage of mappers complete slowly go up, and then the percentage of reducers complete will follow that. Again, running on a local VM, your submission times may be faster or slower than mine. Within a few seconds, you should start seeing some progress being reported back. And again, at this point, our job is submitted into the cluster. So even if I ran a Control-C to kill the command right here, the job would still be running in the cluster. So that's an important thing to note, is if you actually want to kill a job, you need to run a Hadoop-kill command. But here we see that our job completed, and it spits out some roll-up stats about, for example, how many input records were processed. So this is how many key value pairs came in, or really that is how many lines of text were in our Shakespeare dataset. And supposedly it's gone through and done the word count algorithm. Let's not trust Hadoop. Let's actually go ahead and verify this. And we're going to run that with the Hadoop fs command. And we're going to do an ls on our output directory, which was output-word count. Again, this is a relative path to our base directory at /user/Cloudera. Expand our window out here a little bit and run that command again. We see that we've got several outputs that came out. If a job completed successfully, you'll see an _success, and you'll also see the logs, the roll-up stats for the logs for this job submittal. In this case, we see that we got our final output, and we can cat this. So you can go ahead and copy that and do a Hadoop fs-cat command on output-word count /part-r and then 5 zeros. This is indicative of the fact that we ran a map reduce job. So this was reducer output. And because we only see a single file here, we know that we only ran a single reducer. If you ran 5 or 6 reducers, you would see 5 or 6 individual files with part-r 0000001 through 5 or 6. But here we just have a output of a single file, so let's go ahead and cat that out. You're going to see a whole bunch of output fly by, and that maybe isn't so useful to us, but instead we can pipe this to a less command, and then we can page through the results. So we can see that every word that was encountered, in this case, even if it contained quotes around it, we see how many times each individual word in the Shakespeare dataset appeared. Again, we've walked through all the steps required to write the Java code as well as submit our job. Thanks for joining me on this 2-part MapReduce code walkthrough. In the first part, we did these 2 things, looked at the Hadoop jar job submittal command in detail, and in this exercise, we looked at the map code, the reduce code, and actually did a job submittal and looked at our output.